In this video, we'll talk more about the basis for a topology. So recall that if x tau is a topological space, then a basis, beta for tau, is a subcollection of tau with the property that each member of tau is a union of members of beta. That is, beta is a subcollection of T, a subset of the collection of open sets in X, and every open set, every element of tau, is a union of sets from the basis, from beta. So far, we've started with a topology and then found a basis for it. But now we'll look kind of in the reverse order. We're going to start with a basis and generate a topology from it. So when is some collection of subsets of a set X a basis for some topology on X? Here is a theorem describing when that's the case. So our theorem says that a collection beta of subsets of a set X is a basis for some topology on X if and only if the following two conditions hold. 1, the union of members of beta is the entire set X, and 2, for each set B and C in beta and each X in the intersection of B and C, there is a set B sub X in beta such that X is in B sub X, and that is a subset of the intersection of B and C. So let's prove this. First, let's prove in the forward direction that if beta is a basis for some topology on X, then conditions 1 and 2 hold. So proof that 1 is true, that's immediate. Because beta is a basis for some topology on X, let's call that topology tau, then we know that for any topology tau on X, the entire set is always an element of tau. And by definition of basis for a topology, since X is open, X is a union of basis elements, of beta. So X is equal to the union of B for each B in beta, since each B is a subset of X, and X is the union of the elements of B. So 1 is immediate. 2 is very quick as well. So let's let B and C be elements of beta, and X be an element of B intersect C. So since beta is a subset of tau, as each element of beta is also an open set, that means that B and C are open, which implies that B intersect C is open by definition of a topology. Definition of a topological space: finite intersections of open sets are open. And so then, since B intersect C is an element of tau, by definition of basis then, B intersect C is a union of elements of beta, and so there is some B sub X in beta such that X is an element of B sub X, which is a subset of this set B intersected with C, this open set B intersected with C, and so we have shown 2 is true. Now let's do the proof in the reverse direction. Let's suppose that beta is a collection of subsets of X such that 1 and 2 hold, that the union of members of beta is X, and for each set B and C in beta and each X in their intersection, there is some set B sub X in beta such that X is in B sub X, which is a subset of B intersected with C. So we want to suppose these hold and let tau be the collection of all unions of elements of beta. Now we want to show that tau is a topology for X. So what do we have to show? First of all, we have to show that the entire set X and the empty set are in tau. So by 1, it's immediate that X is an element of tau. because X is a union of elements of beta. Now, what about the empty set? The empty set is in tau vacuously. We can think of the empty set as the union of the empty collection, empty subcollection of elements of beta. Okay, so we know that X and the empty set are in tau. That's the first condition to be in a topology. Now, our unions of elements of tau in tau? Yes, this is immediate from just our definition of tau, that tau is the collection of all unions of elements of beta. So any union of elements of tau is a union of elements of a union of unions of elements of beta. A union of unions is still a union, and so yes, any union of elements of tau is in tau. Now the third part, finite intersections. Now that part is just a little bit trickier. Here we actually need to use condition 2 above, and we're going to do it inductively. So let's just first start with two sets. So let's let U1 and U2 be elements of tau. We want to show that their intersection is in tau. So if U1 intersected with U2 is equal to the empty set, then we're done. That's immediately in tau. Otherwise, let X be an element of U1 intersected with U2. So then, since U1 and U2 are elements of tau, this means that both are unions of elements of B, or of beta. Both are unions of elements of beta. And so that means there exists sets B1 and B2 in beta such that X is an element of B1, which is a subset of U1, because U1 is a union of elements of beta. So X being in U1 means there's some basis element containing it that's a subset of U1. And X is an element of B2, which is a subset of U2 for the same reason. So now we're going to apply condition 2 above. So by condition 2, since X is in B1 and B2, these basis elements, there is some other basis element, or some basis element, B sub X in beta, such that X is an element of B sub X, which is a subset of B1 intersected with B2. That's condition 2 above, and we know that each of those were subsets of U1 and U2 respectively, so that's a subset of U1 intersected with U2. So what we see is that for any element X in U1 intersected with U2, there is some basis element B sub X in the basis such that X is an element of B sub X, which is a subset of U1 intersected with U2. Then we can take the union of these basis elements. So then U1 intersected with U2 is a union for all X in U1 intersected U2 of these basis elements. And that implies, by definition of our topology tau, or our hopeful topology tau, that tau is the union of elements of beta. That tells us that U1 intersected with U2 is an element of tau. So now we can proceed by induction. So let U3 be an element of tau. So now U1 intersected with U2 intersected with U3, we could do some associating. So U1 intersected with U2 intersected with U3. We already showed that the union of two sets, open sets, is in tau. So this is an element of tau, this is an element of tau. And by the proof above, the intersection of two elements of tau is in tau. So that tells us that U1 intersected with U2 intersected with U3, which is equal to U1 intersected with U2 intersected with U3 is an element of tau. And we could continue this for any finite integer n. For any n in the natural numbers, U1 intersected with U2 intersected with UN is an element of tau, where each UI is in tau. So we have shown that this collection of subsets of X beta does generate a topology for tau. Beta had those two properties above, and we showed that tau, which is the union of, or the collection of all unions of elements of beta, has the necessary or satisfies the necessary conditions for being a topology on X. Let's use that theorem to show that this collection of sets is the basis for a topology on R. So B double prime is the collection of half open intervals, A less than or equal to X less than B, such that A is less than B and A and B are real numbers. So to use this theorem, we need to show that the union of elements of B prime is the set of real numbers, is the entire set, and that if B1 and B2 are elements of B prime and X is in their intersection, then there's some other or some basis element in B prime, double prime, such that X is in that basis element and that basis element is a subset of their intersection. So let's show each of these pieces. The first piece is pretty quick. To show that the union of these subsets of R gives us all of R, let's show that any element of the real numbers is in at least one of these sets. So let's let X be an element of the real numbers. Then the set X to X plus 1 is an element of this collection of sets, this B prime, and X is an element of X comma X plus 1. For any real number X, X is an element of this union of basis elements, and that tells us that the union of all of these basis elements, A, B, such that A is less than B, A and B are real numbers, does give us the whole real number line, because each of these subsets is a subset of R, and every element of R is an element of at least one of these sets. So the first piece is satisfied. Now, let's suppose that B1 and B2 are elements of beta double prime, and X is an element of their intersection. By definition of beta double prime, B1 is equal to A comma B, and B2 is equal to C comma D for some A, B, C, and D in the real numbers. So let's see, we've got these numbers and we don't know, which one's larger than others. So we might have A and C and D and B, for example. And so we want to find the intersection of these. The intersection, we could take the maximum of the two lower limits and the minimum of the two upper limits, and then whatever that max and min are, the smaller interval is going to be a subset of the other two. So let's let M be the maximum of the two lower limits, A and C, and N be the minimum of the two upper limits, B and D. Then B1 and B2 are both subsets of this new half open interval from M to N. And because X was in the intersection of them somewhere, that means that X is an element of Mn, and this is of the form, half open interval with real numbers with the first less than the second. And so this is in our collection beta double prime. So we've got for any B1, B2 in beta double prime, there exists this beta sub x, this particular one, Mn, that we've just created, such that x is an element of beta sub x, and that is a subset of B1 and B2. So the second condition is satisfied, and therefore that means that this beta double prime, this collection of half open intervals, is such that A is less than B, A and B are real numbers, is a basis for a topology on R, and we can call that the half open interval topology. It's also sometimes called the lower limit topology. So this is a topology on R. Now you might look at that and say, okay, does that give us a different topology than, say, the open interval, than the basis consisting of just open intervals? And so when we think about whether two bases generate the same topology, two bases, beta and beta prime, are equivalent bases if the topologies tau and tau prime that they generate are identical. That is, tau and tau prime contain exactly the same sets are open. So here's a theorem for determining when it's the case that two collections beta and beta prime are equivalent. So they're equivalent if the following two conditions hold. One, for any B in beta, for any B in the first basis, and for any X in that basis element, there is some B prime in the second basis, such that X is in B prime and B prime is a subset of B. Secondly, the exact same condition, just with the roles reversed for B and B prime. So for any B prime in the basis beta prime, and for any X in this basis element, there is some basis element in beta, the first basis, such that X is in B and B is a subset of B prime. The proof of this is going to be a homework problem, but let's do some examples of determining whether different bases give equivalent topologies on sets. Here we're going to look at, first, is it the case that this topology we just looked at, or this basis we just looked at, and the regular open interval, the regular topology generated by open intervals give equivalent bases for topologies on R? So that's our first question. And secondly, if we look again at our usual basis for the usual topology on the real numbers, the open intervals, does that give us the same basis if we were only looking at rational endpoints for those open intervals? So think about each of these in the context of that previous theorem. Take a pause and we'll talk about them together. So is this first pair of bases for topologies on the real numbers a pair of equivalent bases? So as above, we'll call this beta double prime, and we'll call this one beta because it's the basis for the usual topology on R. So in this case, our answer is no, and our issue is going to come with this closed part of the interval. So let's just consider some example. Let's consider the half open interval from 1 to 3. That is an element of beta double prime. Now 1 is an element of this half open interval, but let's suppose that 1 is an element of AB for some AB in the usual basis for R. Then, by definition here, 1 is between A and B, so 1 is greater than A and less than B, and that tells us that this open interval AB cannot be a subset of the half open interval from 1 to 3, because it's going to contain some elements that are less than 1. So that tells us that there is some element of beta double prime and some element of it, such that there is no B in beta, such that 1 is an element of B, which is a subset of 1, 3 equals B double prime. So that tells us that these are not equivalent bases. For our second example, we'll again call the usual basis for the usual topology on our beta, and we'll call this one with rational endpoints beta prime. So if AB is an element of beta prime, then AB is also an element of beta, because if it's a rational number, then it's also a real number. So one direction here is clear. X, an element of B prime in beta prime, implies that B prime is in beta. So, we're good to go. This X is an element of B prime, subset of B prime, and this is in beta and this is in beta prime. So one direction is clear, or the first condition is clear. With the reverse roles, let's let A, B be an element of beta. So A and B are real numbers. A is less than B. Let's let X be an element of this open interval from A to B. Then by definition, A is less than X, which is less than B. And we know that the rationals are dense in the real numbers. So we know that there exists R and S in the rationals, such that A is less than R, which is less than X, and that X is less than S, which is less than B. So this tells us that then R comma S contains X, and that's an element of beta prime, such that X is an element of this basis element for beta prime, and that's a subset of our original basis element. And so yes, these two topologies these two bases do generate the same topology on R. So beta and beta prime generate the same topology on R.